f of x, yeah, because f is multiplied by p, f of x m gamma divided by d. Then this is a very simple equation, because log of p is like the integral over x f of x m gamma d. dx. And what is the integral over the force, the deterministic force? It's nearly the potential. It's minus the potential, because, yeah, you got it right. So this is minus the potential m gamma tilde d. So P equilibrium, this is the equilibrium. P equilibrium, if I believe my equation, is some normalization. We don't care about this normalization. Exponential minus u of x m gamma d. But we know what is m gamma d. What should this junk be? That should be kBt. So mathematician would say this is not a proof. This is a physical proof. We know the solution. We believe more in Boltzmann equilibrium than we believe in this equation. So we know that the system, or we assume the system goes to that equilibrium. And then we know something, which is, again, this is the Einstein relation that we got already previous class, but in a different way. What do we know? We know that K Boltzmann T is equal m gamma d. So Einstein preferred to write it a bit differently. K Boltzmann T m gamma tilde. So the diffusion constant is related to temperature and the friction. If you know the temperature, you know the friction, you know the diffusion constant. And that means, I told you before, measure MSD x squared as a function of time, get diffusion constant. You can do that. Let's say you did it, then you know what is this friction, if you know the temperature. You can also measure the friction directly, because now it's real. If you believe Stokes' law, you know exactly what this is. If you know the radius of the sphere, if you know the viscosity, you know exactly what this guy is. So in that sense, we know d. If you can measure the size of the particle, you can measure the viscosity. Stokes gives you this guy, and then you know the diffusion without measuring. So that's already a theory, if you want. It's a theory which connects between things, but doesn't calculate each one of them individually. It's not a microscopical theory. So now, going back to the Fokker-Planck equation, I can write it again. Because I have this relation, I can write it in two ways. What do you mean I can write it in two ways? I identified what's A, I identified what's B, and now I also identified the coefficients d and gamma. So I can write the Fokker-Planck equation like dp over dt 1 over m gamma tilde dx. This is the derivative with respect to x. This is the minus the force plus K Boltzmann T second derivative P. That's what I did here is, you remember this B over 2 was D. So I simply wrote what is D. This is what I did. You see, K Boltzmann T over m gamma is equal D. That is what I called half Bx at the beginning. And it's independent of x, of course, because we assume that. So I simply plugged in what is A. A is the force, It's related to a potential, so I wrote the potential. I could write the force, of course. I can also write this slightly differently, dp over dt equal d. So I can take, here I'm using the friction because let's say I'm Stokes, I know the friction. And let's say I know the diffusion constant, I can write it the same way. This is second derivative with respect to x minus d over dx, the force, divided by k Boltzmann t, p. This form is slightly more popular, but it's the same thing. So here I use d, here I use gamma, but they are the same thing, so I can use either this is the derivative, or that is the same thing. Let us use this equation. Now I want to derive not the relation between friction and diffusion, but I want to derive again. I want to derive, it was in last class, but we are repeating a little bit. I want to derive the mobility of the system. What is the mobility? I apply a constant force. Very simple. If the force is a constant, so my potential ux is equal minus force times x. It can be mg, it can be a charge times an electric field, whatever you want, but this f, this small f, is independent of position and independent of time. It is a constant. Then we know that x dot from the Fokker-Planck equation is 1 over m gamma tilde. And you see here, I have this force. So I have integral from minus infinity to infinity. I'm integrating over the density. Here I have the force with the sign, with the minus sign, because here you have the derivative of the potential. So this is this minus sign. And here I have this P. And I use the fact that here I have the second derivative, and that when I integrate that, I get the first derivative, and on the boundaries, that gives you 0. So I'm doing here, I'm already omitting this friction, and this is because of the very specific observable, the average, and the specific force I'm using here. This is simply, what is this guy? I'm not proving this to you, but this integral, what is px t dx? That's very simple. Integral from minus infinity to infinity. That is simply 1. That's the normalization. The total density is not changing in time. I didn't prove it, but you can show that this is correct. And then you have here simply, but wait, you have here, I made a mistake here. Here I have, sorry, this is d over dx. This is important, of course. This is this d over dx. So I have the force d over dx. So I have here, and then I do integration by parts. So this minus changed to a plus, and then I get f m omega gamma. Yeah. So this is the time derivative of the position. So what is the position itself? Let's say you started at some point we call 0 on average, and this is average x. I integrate over time, but this is a constant, so it's trivial. F m gamma tilde times t. It increases linearly in time, t. What is the MSD? This is the fluctuation, x squared average. But when? When the force is 0. This, as we know, I said about 1,000,000 times, is 2 dt. This is just the diffusion. When you don't have this thing, then you just have this thing. There's no force. So here I have x, if you want to add a small f here. This is the response of the system to a force. You have a net drift. It's trivial because you have friction, and you move with a constant velocity. The stronger is the force, the faster you move. On the other hand, you have MSD with no force. But these two guys, M gamma and K Boltzmann T, are related. So we can say the following, that the average position in the presence of the force, when force is not equal to 0, is equal to the MSD when the force is 0. Because you see, this is T and this is T. And then I need to, this is proportional to F divided by 2 K Boltzmann T. What did I use here? Of course, I used this Einstein relation. So the 2 kills this 2. And then you get here D over K Boltzmann T. And D over K Boltzmann T is 1 over M gamma. This is an Einstein relation, but Einstein did not write it like this. You can ask, so why do I write it like this? Because actually this is more general than Einstein. For example, this is valid if x goes like t to some alpha and MSD goes like t to some alpha. This is something called anomalous diffusion, which came much later. And then this is the form of the fluctuation dissipation. The relation between the response to the field and the fluctuation is here. More generally than Einstein, while if you have here, let's say, t to the half and t to the half, the diffusion constant is actually not well defined in the usual term. So, but this is something you cannot see right now. I'm just saying this is slightly more general than the usual thing. But the usual thing would be, or Einstein's thing, is very simple. Where? Here? No, it's the complete opposite. It's the mean. That's the whole point. So the point is like this. Again, I repeat myself. You perform an experiment when you have an applied field, and then you see, if this is not clear, then nothing is clear. Then you have these trajectories. They are random. And there's a force in this direction. So you have also the average. The average is something like that. And this is x as a function of t, as if t is going like that. This is x of t. So t is increasing, and then this is position. So the particles were here. So this is actually position in space. This is the starting point, and this is some end point, and you are moving in that direction. So you are moving with time. So this is time going up. Then you measure the average. You get the average of x. Every or many condensed matter experiments are like that. What is this average of x? It's simply if you have a current in your system, let's say these are electrons. These are simply, the force is the electric field, and then they are moving with a velocity. This position is the velocity times t. Then you do a totally different experiment. You do a different experiment. You again measure x as a function of t. But now the force is 0. And then this is trajectory of one particle. It goes to the right. This is a trajectory of another particle. It goes to the left. Here you have some Gaussian distribution of particles. They all started here. Here you measure x squared. The average of x here is 0, nothing. There's nothing to measure here from the point of view of the average. You measure then the fluctuations, because here x is equal 0. Here you measure the force moment, which is not 0 because the force is not 0. And the claim is that this guy and this guy are related. This guy is increasing with the force. The bigger is the force, the bigger is this guy. This guy is something. You divide by temperature and you get this guy. That's the claim of Einstein. So in this experiment, one can also go back to the derivative of the force, and then you get simply something which is called mobility. Mobility is what you measure when you want to measure conductivity. Essentially, this is Ohm's law when you measure the response. So this is the velocity of the particle. The velocity is proportional to the force and some property. This property depends on the medium. But now we know exactly what this property is. It's related to the diffusion constant. So for example, you have electrons and you apply an electric field. You get a net drift. They are moving. Depending on how strong your field, they move faster. Right? That's obvious. This F is obvious. You get this coefficient. This coefficient is a monster. It depends on temperature. It depends. It's very complicated. There's millions of articles. What is this? Mobility for different mediums, for this system, for that system, for that system, at low temperatures, at high temperatures. Very complicated function as a function of, let's say, density of scatterers, of temperature, of many other parameters of the system. But no matter what, this mu is related to d, which is again a complicated function. So we don't know what this guy or this guy are independently in general. We can measure them. But we know that these two guys are related. And the relation is, of course, that mu is equal d divided by k Boltzmann T. Going back to theory, what you see in many theories, because see, this problem is much more complicated in principle than this guy. Why? Because here we have a force. So let's say you have some molecular dynamic simulations. You need to apply a force and then see how you move on average. Then you want to calculate this response, the average speed of the particle. You calculate mu from a very complicated, let's say, simulation or even in an experiment. It can be difficult to measure with a force. Or maybe not, but let's say in a simulation you need to add this force. What is Einstein telling you? You don't need to add the force. Do an experiment without the force or molecular dynamic simulations on your computer. Measure d. And then if you know d and you know the temperature, you know the mobility. Without adding the force into your molecular dynamic simulations. And this is what exactly people do. When they do theories, they usually calculate this diffusion constant and then they say what is the mobility. Mobility is for many technological applications very important, because you understand why. Because this is the conductivity. Because if you have some circuit, you have some material, you want to know if the mobility is strong, then you move fast, you are happy. If the mobility is very low, that means you are practically an insulator, etc. So again, all condensed matter physics is on the question, what is this mu? Then this thing is a very useful relation in order to understand this better. So, okay, so here I just re-derived the Einstein relation, again expose you again to the Fokker-Planck equation and started with the Langevin equation. What we'll do after the break is I'm going to show you very, I would say briefly, not in depth, how do you solve this equation? Okay, I gave you an equation, but how is it solved? I'll show you one technique. There are many techniques. Mathematica? If you don't want to understand, use Mathematica. But if you want to understand, you better, in some cases at least, use other methods. So, yeah, but indeed, Mathematica can many times help you. So in the break, one of your friends found a mistake, a very tragic mistake. Here I forgot the x. So remember here I calculated the average of x, so I multiply this function by x. I multiply by x, and then I integrate, and then I need to have an x, and then when I do the partial derivative backwards, I get this result. Because otherwise, if you have just the derivative of x, then this integral gives you 0. Let me just show you, because maybe it's not clear, with a different example. So what am I doing here? This is a very simple trick. So we have dp over dt equal gamma, they're just copying this equation, d over dx, u prime plus k Boltzmann t, second derivative of x. All this is operating on p. I want to emphasize again, this derivative, you see here I have a derivative of u, it's just the force. This derivative is acting on this guy, but it's also acting on this guy. So it goes through everything. It's an operator language where this d dx operates both on the derivative of the force, also on p. That's first of all. But what I do in this example, I multiply equation by x and then I integrate. Let's see what happens if I don't integrate, don't multiply by x, but just integrate. If I integrate, I get here integral dp over dt dx. This is simply the time derivative of px of t dx. If this is a constant, that is normalization, we claim this is 1. When is it 1? When initially the PDF was 1. If it's normalized at time t equals 0, it's 1. This should be equal 0. And this is easy to see from the other side of the equation, because I have here, this on the other hand is equal to the integral from minus infinity to infinity dx, 1 over m gamma d dx u prime plus k Boltzmann t, second derivative, all this is acting on p. Now, it's trivial to see this is an integral. This is the mistake I did before. I didn't have this x. This is what I had before. So you easily see what is this integral. It's an integral dx of the derivative of something. This something is 0 at plus minus infinity. So this gives you 0. This is also a derivative of the second derivative. Integral over the second derivative. That gives you the first derivative. But also that is 0 at plus minus infinity. So this is obviously easily seen to be 0. And this means that you conserve normalization. Now you do the same. This is what I tried to do here, but I missed a step. I missed this x. So if we do exactly the same, but now we multiply the function first by x. So I have x dot. That is, by definition, x p dot dx. That's the average. That is equal to d over dt x px over dt. I can take this outside of the integral. So I know what is this guy. This is simply the solution of the Fokker-Planck equation. So I just multiply this side by x. Integral from minus infinity to infinity dx times x m gamma, this is this one, d over dx u prime plus k Boltzmann t, second derivative acting on p, and it's px and t. For any time t, this is valid. Then here, what I do is integration by parts. I go backwards. So this guy will give you 0 because when I do integration by parts, I'll get this done and then I'll have the first derivative and then p at infinity is 0. So this guy is equal to minus integral dx. I took this away and then I have u prime m gamma times p dx. The dx is already there. In our case, this u, this was simply minus u prime, that's the derivative on x, was simply f, the force, this small f. So here I have simply f divided by m gamma tilde, integral over p dx. But this I proved you here. This one is 1. So we get what I said in previous class, f is equal f divided by m gamma tilde. This result. But you see, here I did it in one line, and here I did it in several lines, including proving the normalization, which is used here. But the normalization is obviously trivial. I mean, obviously this integral has to be 1. Okay, this was a technical point. Now we're going to go to another technical point, but a bigger one. So we want to solve the Fokker-Planck equation in generality. And to do that, we transform it to a very famous equation. The famous equation is Schrodinger equation. So this equation, you already see if I have a second derivative, it's like kinetic energy in Schrodinger equation. If this is independent of x, at least this is obvious. Then you have another thing, well, this is not so similar to Schrodinger equation, but we can do it with a trick. We can transform this equation to the Schrodinger equation. Why is this useful? Because you are experts on the Schrodinger equation. You know how to solve Schrodinger equation. You know how to do perturbation theory. You know how to do eigenfunction expansion. You know many things about the Schrodinger equation, and that's one reason. There's a slightly also interesting reason is that there is, of course, a fundamental difference between the Schrodinger equation and these type of equations, that in the Schrodinger equation you have here an I. Then, of course, this I is you can say this I is the whole difference between stochastic theories like this and quantum mechanics. This I is super important because this gives you that the nodes of decay, eigenvalues, are in Schrodinger equation, they are real. These are the energies of the system. Here you'll have decaying modes, no oscillations, but decay. So roughly speaking, in quantum mechanics you have, in a time-dependent problem, you have the eigenvalue, the eigenfunction times the exponential of I, energy times time. You need to sum this over all the eigenfunctions, and then you get the time-dependent solution of the Schrodinger equation. Here you have something similar, but instead of oscillating functions, you have decaying functions, and they are decaying exponentially. So all decaying in time. So all the modes are decaying in time. Why? Because you have dissipation. So you don't have oscillations, you have decay in time. But otherwise, there are some similarities with the Schrodinger equation, which I want to make more clear now. So we are going to work with this equation. It can be made more general. If b is depending on x, you can do this transformation, but it's a bit more of a headache. This mapping, for example, exists in a textbook called Risken. Risken does it for general B and general A. Here we have D, which is independent of X, and force and temperature to make it slightly more physical. But you can do it for any set of two functions. So the first thing is to define an operator. So just copy this into your text, your notebook, and then we're going to write this as L Fokker-Planck P. So what is L Fokker-Planck? This is simply all this junk. This is called the Fokker-Planck operator. It's the center operator. You know, in analogy, in quantum mechanics, what is the most important operator to describe the time dependence? You see the time dependence is H, the Hamiltonian. But these are very different operators because H is Hermitian. While this operator, L Fokker-Planck, one can show is non-Hermitian. So what we are going to do now is we're going to do a trick to solve to switch the problem into a Schrodinger-like equation where you'll have here a Hermitian operator. And you know, Hermitian operators have many good things like eigenvalues are real, etc., many good properties that you learned in quantum mechanics. So this is very advantageous because you can say something on the dynamics of the system. So the general measure, not surprisingly, is separation of variables. And the idea is, okay, let's see if I don't make a mistake on the way. P xt, because I called it W, but never mind, is equal phi of x exponential minus lambda t. So what is this solution? This is, of course, a very specific solution. We don't specify what's the initial condition. This guy is an eigenfunction. I'll soon define it. Eigenfunction of the Fokker-Planck operator. And this lambda is the decay node, the decay rate. Decay rate of what? Of the specific node. So like in quantum mechanics, you have think about harmonic oscillator, you have many eigenfunctions and many energies. So for each eigenfunction, you have a different rate of decay. We want to calculate this rate, and we want to calculate this function. And there will be a family, and there will be something like a quantum number if you want, or there will be spectrum. Spectrum can be continuous, spectrum can be discrete, or a combination of discrete and continuous. But this is essentially an ansatz where I separate variables to phi of x, some function of x, and a function of time. Of course, you could do it here just plotting some function of time, but I already plotted, gave you the exponential. Why the exponential? Because here I have the first order derivative. So it's very easy to see that this is, with this ansatz, you separate the variables. Now, just to remind you, this is a particular solution. If you want a solution that depends on the initial condition, then you need to specify the initial condition. Let's say a delta function in space somewhere, a particle starts somewhere. And you need to sum an infinite series of these guys. Okay? So I'm not talking about that solution. I'm talking about the eigenmodes and the eigenvalues. Later on, I will not do it actually here, but I'll give you the full result. What is P, which depends on specific initial condition. This is just a solution independent of an initial condition, independent even of boundary condition. This is just phi of x. Not independent of boundary condition. And again, we want to find these two guys. So this is kind of easy, because if I take I just plug this into the Schrodinger Fokker-Planck equation. When I take the derivative dp over dt, I get a minus lambda times phi, and this Fokker-Planck operator is not operating on the exponential decay. And then it's very easy to see that the equation is L Fokker-Planck phi of x equal minus lambda phi of x. This is the equation. And the nice thing here is I don't have time. So if I solve this equation, and again, there's a spectrum of functions, there is a spectrum of solutions, so we can say, for example, if the spectrum is discrete, you'll have here a quantum number n, and here a quantum number n. If you can solve this equation, essentially you are done. Well, except for the problem that this is not Hermitian, so you don't know if it's complete or not complete. Remember that in quantum mechanics we use Hermitian operator as H, and then we could say we can decompose any initial condition into a linear combination. We don't want to work with this function, with this operator, we want to transform it, and that's the next step. There is a small issue. Here I add a minus. Why minus? Because I'm expecting relaxation. I'm not expecting something that will grow with time. What will be the ground state here? Can someone see what is the ground state here? Let's say you have some binding type of potential. What is the meaning of the ground state? Or can you tell me anything on the properties of these lambdas? Let's say you are in a force field that is binding. What do you expect? These lambdas, can they be negative, first of all? No, they cannot be negative because then this will explode in time. But you know even something more. You know that one of the lambdas has to be 0 because you have to go to the ground state, which is not changing in time. And this we will see later on through an example, that one of the lambdas, if you are in a binding potential, is 0. It's not trivial. And it's not trivial that all of them are positive, but this is what we expect physically. So let us treat problem after problem. So first of all, how do we reformulate the problem with a different operator, which is much closer to the Schrodinger operator? This is done by a simple transformation. Instead of this function phi, we're going to use a function psi. Psi n of x. Again, n is the quantum number. It can be sometimes discrete, sometimes continuous. I'm going to use n. But I hope you understand that if this spectrum can be discrete or continuous, then this number can be discrete or continuous. We are also looking what are the possible values of n. Again, this will come later. So what we do first is we define this wave function. So psi is like in quantum mechanics by phi n of x, e to the power u of x divided, here there is a 2, a very annoying 2, but without it we cannot do anything. So here there's a 2. And what you have here is the potential, the equilibrium potential that gives you the force divided by k Boltzmann T. Then I claim that L, this is not the Fokker-Planck operator, this is a different operator that I'll soon write. Phi n is equal minus lambda psi n. This is the equation I will solve. This is the eigenvalue problem. It's the same lambda as before, but the functions are different. But of course, if I find this function psi, I know this function phi. So this doesn't cost you much. This is just a transformation. And what is this L? It's of course related to the Fokker-Planck operator, but it is given by this transformation. 2, here I have k Boltzmann T, L Fokker-Planck, e to the minus u of x, 2 k Boltzmann T. So soon we are going to treat this problem. And at the end of the day, we transform. And here we have an operator which I'll soon show you why you like this operator and not the original one. Maybe you hate both, but when I mean like, I mean it's more familiar. Not at this stage it's familiar, but soon it will be familiar. So let us see what I did here. Up to now I did something very simple. I mean, I did the following. I simply did the following. This is definition, this is just a definition. So what I did is, let us look what is phi. I just invert this equation. It's very simple. It's e to the minus u over k Boltzmann t over 2. This plus, I'm going to just take it to the other side, that's all. Psi of x. Maybe now it's already a headache. K Boltzmann is going to be 1. So every time you see K Boltzmann T, I'm just going to write T, the temperature, but it's in units of K Boltzmann. So, this I know that the Fokker-Planck operator acting on phi n is minus lambda phi n. That's just my definition of lambda and phi n. This is equal to L Fokker-Planck operator e to the minus u over 2t psi. This I just copied this definition. Minus lambda e to the minus u 2t psi. Now I just multiply this equation by e plus u over 2t. So then I get e to the u 2t L Fokker-Planck e to the minus u 2t. All this acting on psi is equal minus lambda psi. And this is what I called L. This is just the definition of L. This is L. Without, here I have the subindex FP, Fokker-Planck, here I don't. So we have L psi n as before, minus lambda psi n. We are happy. So up to now it was just simple massaging and transformations. Now we have to see why the hell I did this. I mean, why is this transformation so nice? For that, unfortunately, we need to work a little bit, not too much. And we want to see what is this L. In terms of what? In terms of the force, in terms of the diffusion constant, instead of the temperature, in terms of the temperature, what is this L? I mean, what am I doing here? I'm just explaining you what is L Fokker-Planck for 1 hour, and now I'm going to a different operator, L, which is different. And why do I do this? So for that, let us write what is L. U over 2t times d, d over dx. So this is the Fokker-Planck operator. Here I have d over dx minus f, which is a function of x, k Boltzmann t, e to the minus u 2 times t. Of course, this is an operator, so what I mean here is that this function, if you put something on its right, everything is acting on it. So this derivative is acting on this force, it's acting on this thing, but it's also acting on a function that is here. What will be the function? The function will be, of course, for example, this eigenfunction, or the density itself, etc. So we have here an operator. Like in quantum mechanics, we have to treat it. That means we read it from left to right as usual. So now, here again, let me emphasize this. All this junk is the Fokker-Planck operator, right? So for example, you have here d second derivative, that's the diffusion. And d times the force over k Boltzmann t, that's the drift. So I just plugged it in here. And of course, this force and this potential are related to one another, because minus the derivative of the potential gives you the force, like in Newton's mechanics. This is the deterministic force. So let us see what this is. This is e to the u over 2t d over dx. So I'm just taking this derivative for now. So when I take this derivative, I get like this. I get 2t, because when I take the derivative of an exponential, I get 2t. And then the derivative of u with the minus sign, that is the force f of x. And then I have also this term. I have here f of x divided by t. kb is 1. All this times e to the u over 2t, this guy. But I have another term. You see here I took the derivative of this, right? But this guy also operates on the other side on the function that is here. This guy is equal plus e to the minus u over 2t d over dx. In other words, of course, all these operators are not commuting, etc., etc. This guy is e, let's copy this, 2t d over dx. Here I have this minus f over 2t. So you see it's half minus 1, and actually this half is going to be later important. E to the minus u over 2t plus e to the minus u 2t d dx. Now I need to take the second derivative, the second time, the spatial derivative. So all this guy is equal e u over 2t. This is just this term times d times. You see, again, this d dx, when it operates on f, it gives you derivative. It operates here, it will give you another force, but it also operates to the left. So from this term, we have 3 terms. So here I get minus, when I take the derivative acting on f first, f derivative, this is this derivative over 2t. Now I have, when I take the derivative here, what do I get? I get derivative of u, that's the force. And again with this 2t. So then here I get plus f squared over 2t. All this e minus u 2t, e minus u 2t. You see now what will happen with this 2t. It will cancel with this guy. So this exponential will eventually decay because we multiplied the operator from both left and right by exponential of something and exponential of minus something. Now I have here also minus f over 2t e to the minus u over 2t d over dx. This is simply when this guy is acting on the function, so I'm just taking it to the other side. And now I need to do the same here. I have, when this guy acting on this guy, then I have a plus f 2t e minus u 2t d over dx. The nice thing, you already see the nice thing, or one of the small wonders of nature, but not really. This guy and this guy go away. They are the same. Okay, so this was this guy acting on this guy, and then I have this guy acting on the second derivative. Then I have plus, let's write it here, e to the minus u over 2t second derivative. This is simply this derivative. Again, operating on this times a function, so you have also this second derivative here. So First of all, I hope you all see that because of this guy, all these exponentials go away. Because again, here you have plus, here you have minus. Here I have second derivative with respect to x times d. Maybe not so impressive, but let us anyway write it. This is the second derivative with respect to x. And what is the point of all the transformation? What is the remaining part? You see it's this d and all this without the u's. What is this? It's some function of x. That's the point. So I can call all this function of x, what will I call it? A potential. What is the potential? We call it Vs. So here I have minus Vs of x. So this is my L. S is for Schrodinger. So we transform the Fokker-Planck operator into the Schrodinger operator. And now we have a potential which is complicated. It's related to the force. Let's write it explicitly. What is the potential? Vs of x is equal d, because of this minus sign. So d, the derivative of the force over 2t minus the force over 2t to power 2. This is the potential that we need to work with. So not to be confused, of course, we have two potential fields. One is the real potential, which is u, and then another effective potential that goes into the Schrodinger equation, which is given by this force over temperature and by the diffusion constant. This is not something intuitive or something easy to understand. What is the meaning of this potential in the Schrodinger language? But this is just a transformation. Every problem you give me, every force you give me, which is not zero. So, for example, if the force is 0, then obviously you only have this diffusion, so this goes away. If the force is a constant, this guy goes away, and then you have only this guy. This is a constant. So if this is a constant, actually it doesn't influence much the Schrodinger equation because it's just a shift of the energies. That's a little bit subtle, actually. What is the units of V? So the units of V this is easy to see. So units of V are, you see, force divided by temperature. That's 1 over x, because temperature is energy. Energy is force times x. So F, so here I have simply d times 1 over x squared. But d is x squared over t, so this is 1 over time. And the same if you do here, good that I'm checking. Here I have a mistake. This is this d. This d here. D has to be in front of everything, right? So here is d. So here I have f over t, that's 1 over distance squared. This is distance squared over time. This is also 1 over time. And this is, of course, the correct units, because what is lambda? Lambda has units of 1 over time. So if I add this equation, lambda psi, excuse me, the new operator L, psi n, lambda, lambda has units of 1 over time. Also, this operator has to have units of 1 over time. And it's like energy. I mean, energy in units of h bar equal 1 has units of 1 over time. It's the same type of thing. Okay, so we were able to map the problem. To a quantum problem. Because L is given by this thing. This is like What is this in quantum mechanics? This is like potential, this is like the kinetic energy. So if you want h squared over 2m is this d, and v is the potential. So we don't have an h, but for example, we know that when you have h is small, we can use WKB. All these type of approximations, all of these work here. Small h means small d. So we can do expansions and whatever you like, you name it. All these techniques, these are wonderful things. So let us see now, let us see this in an example. What is the simplest example? Harmonic potential. Harmonic potential, I mean, harmonic potential in the original problem. So I think about potential v of u of x is half m omega squared x squared. This is the spring constant, and I have here a Brownian motion inside this confining field. This was the example I showed you before of a particle on a spring in water, and you look at the position of the water, how it fluctuates with the restoring force. This is, you can say, very easy problem because the force is linear, so let's look at this one. Okay, so this is my u of x. It's a function of x. Let's say the minimum is at 0, what I call 0. What do I need to do? I need to gain intuition on what is this crazy potential. To do that, I'm going to change a little bit notation. I'm going to write, it will be slightly simpler later on, d times ux over k Boltzmann t. I'm going to call this f of x. This is not a force field. This is just a function of x. And this transformation is common. People use it a lot. It's just rewriting this in different ways. So in this case, we have this v of s. Let's look at this. This v of s is d f prime, which is taken from this potential, 2t minus 1 over 4 f squared t squared times d. This I can also write as vs of x. Let me just write it, and then we will see 1 over 4 f derivative over d plus a minus half f second derivative. It's simply a way, you see, instead of to carry all these numbers, I carry only one function. You see, f, just the philosophy, f is proportional to the potential. The force is the derivative of the potential. So when I have here, I have here this squared, you see this is proportional to the derivative of the potential squared, which is the force squared, which is this term. And this 4 is here. And yeah, I made a mistake here. Here I need, this is plus, and this is minus. Because of this minus here. For example, let us look at the derivative of x. This is the second derivative of f derivative. What is the derivative of derivative? It's d u prime over k Boltzmann t d over dx. This is minus the force, so this is d f derivative with the minus sign, k Boltzmann t. K Boltzmann t. So 1 minus 4 f derivative, no, sorry, the other term. So half f double derivative is simply equal to minus d fourth derivative 2k Boltzmann t. Which, do I'm missing a sign here? D where is the sign problem? There is a sign problem. D over k, here I have a minus sign here. So where is my mistake? Where is my mistake? Well, I don't know where my mistake is. Minus here. No, here I should have a plus according to my notes, and here I should have a minus. And then we are okay, because the second derivative is minus df prime 2k Boltzmann, and then if I have a minus here, then I go back to here. Right? Yeah. But then I don't see this minus sign here. So maybe there I have also a mistake. Okay, this minus sign gives you this, but the question is this correct? This is half. Do I have a minus here? This is f minus f derivative, no. Yeah, okay, yes, this is okay. Because the first derivative is derivative with respect to u, and that's minus the force. Which gives you, I think, this minus the force. Yeah, you see here, when I take the derivative of this function, to get the force, I need a minus. So this equation is correct. No. This is minus here. This cannot be minus because it's squared. Is a minus problem. Okay. This is correct, I'm pretty sure. This is plus. It's like this is f here is. Why don't you correct me? No, this is minus. Okay, I have a question mark on the fourth, on the sign. I have a question mark on this. I can't see this. There's a question mark on the sign here, but this is correct, and I don't see why this is correct now. No. Okay, there is a problem with the sign. I can't see it right now, but maybe some of you can see it. I don't see it, actually. But we will continue anyway. I'll have to check this. There's some problem with the sign. I guess it's a silly problem. If we use this equation, just let us check what is the potential. I just take the derivative of f based on this definition. So what is the derivative? It's simply, let's write f again. It's d times k Boltzmann t times half m omega squared x squared. Okay, so again, I have a lot of junk, so I'm just going to write it as gamma x squared. All this is gamma, d m omega squared k Boltzmann t. So then the derivative of f with respect to s is simply gamma x. And the second derivative is gamma. So then the potential is, the Schrodinger potential is 1 over 4 d gamma squared x squared, this is just this term, minus gamma over 2. What is this potential? Do you like this potential? This is simply the harmonic potential of the quantum problem. So what happened here? The quantum particle has the same potential as the original problem. The original problem was harmonic. Also this is harmonic, x squared. And this is like the quantum spring constant. There is a small difference which is very important, and this is the shift. Minus gamma over 2, a shift. What is the shift? This will be corresponding to the zero energy shift. Remember the half h bar omega. Because in the quantum problem, the first eigenenergy is half h bar omega. But I told you before, it cannot be that the first eigenvalue here, the lambda, will be something finite, because then everything will relax to 0. Remember, all the modes are phi x e to the minus lambda t, and then I need to sum all over them. So if all the modes, all lambdas are positive, then at long time, all of them will go to 0. But that's impossible because of normalization, because you have to go to something which is the equilibrium. So this small shift of the energy is going to be important in everything that follows. It ensures the equilibration to the correct value, which is the Boltzmann equilibrium. This will show soon. So but now we are in a quantum this I hope all of you understand is a quantum problem. What you do now, it's really technical. We define some psi, which is square root of gamma 2d times x. Just go to some dimensionless variables. And then you define creation and annihilation operators like in quantum classes. It's the same, very similar. Half d over d psi plus psi and b dagger 1 over square root d over psi minus psi. So you see the multiplication of these two guys give you second derivative with respect to psi. Psi is x. That will be this in the Fokker-Planck, this operator which represented kinetic energy. And then you have a plus and a minus, so when you multiply, they go away. Of course, there is a commutation relation related to this guy. I'm not going on to the detail. And then you have another term, psi squared. The psi squared will be corresponding to this term. And the commutation relation will give you this number. because these two operators are not commuting as usual. If you do all that slightly carefully, the transformed operator is very simple. It has units. This is 1 over gamma. This is the correct units. And then it is simply B dagger B. So this is exactly like the harmonic oscillator without the shift. Usually B and B dagger are called A and A dagger. It's the same thing, but you always have the shift half h bar omega. Here you don't have a shift because we are dealing with a classical problem. And we all know what are the solutions of the Schrodinger equation of the, I call this L, this is like H. What are the solutions of this problem in space? These are the Hermite polynomials, famous solution of the quantum problem. So we know this. We know how to solve the problem. So what are these psi n's? These are given by the following thing. If you normalize and you take care of everything correctly, gamma over what? No, because we are classical. So it's not that the sum of these two guys gives you, why do you want I? There's no I. Yeah.
But the constant problem is as x squared here is minus x squared, so we can only to I.
You're right. There's no I. How will I explain it? There's no I. So the analogy, you see it better in the function itself. You don't need I here because, you know, why do you have I in quantum mechanics? Because of the operator P is minus I h d over dx. Here you don't have anything like that, I would say. But you are right in your point of view to say, how do I see that these are Hermitian? I didn't say these are Hermitian, I said L is Hermitian. And this is because also related to this energy shift. But your question is indeed good. I mean, you don't see it immediately, but maybe I said it's creation operators, this was wrong. This guy will be Hermitian. Not these guys are not complex conjugate, but they are still, we use this B and B prime. So if you do all that, then you get this 2 to the power n, n factorial. H n this psi e to the minus psi squared over 2. Which I'm not showing you in detail. I'm just giving you a hint that these are the Hermite polynomials and these are like the ground states. And what are the eigenvalues? These are the most important thing. Maybe these are simply gamma times n. And n is equal, like in the oscillator model, like this. There is no shift. You see here, the lowest eigenvalue is lambda 0 is equal 0. There's no shift because you see here, there is a shift in the Hamiltonian. Well, it depends what you mean by no shift. There is a shift compared to the quantum problem, yes, but no shift compared to the 0. What I mean by this is in the quantum problem, I consider this as a shift. It's a shift from the minimum, which is in the classical world 0, right? This is a shift. This shift doesn't exist now.
But we said that lambda, not all the numbers can be positive because otherwise for the long time.
All of them are positive except for one, which is 0. And this one, which is 0, is giving you the correct equilibrium. And why do we have one which is 0? Because we don't have the shift in the Hamiltonian. You don't have here the plus. So you shifted the spectrum of, this is the quantum problem, and now we have a problem where you have a ground state, and the distances are these gammas instead of h bar omega. And this omega, yeah, I mean, this is very confusing, but the spectrum is equidistant, like in the quantum problem, but the zeroth energy is the ground state, is 0. Here, you plug in the definition I had before of psi, which is proportional to x, and then you get this function. I didn't want to write all the prefactors. Psi gives you something which is dimensionless, so it's easy to work with. Let us understand better this lambda 0. Only that and that. Of course, now we just did half the job because, okay, these are Hermite polynomials. Each wave function has a eigenvalue, great. But now we need to go back all the way. We need to go and change this psi into phi. And after that, we need to sum up depending on the initial conditions. So there are prefactors which depend on these eigenvalues. But these guys form a complete set. So I'm not going to go into all the mathematical details because they're very similar to the quantum ones. You write down the solution at time t equals 0, and you expand it in this set, and then you evolve it in time with the lambda. If you do all that, you get this solution. This is a solution that you started on x0, so a very sharp initial condition. It's a sum over n. Now we understand what is the sum over n, for example, in our problem from 0 to infinity, but generally on quantum numbers. It could be an integral, but that's if the spectrum is continuous. So, for example, if you have no force, the spectrum is continuous also here, because the operator is simply the Laplacian, like in the quantum problem. All this potential is 0, and then the spectrum, what is the spectrum of a free particle? It goes like k squared, and k can be anything from minus infinity to infinity. That's the energy spectrum, which is not discrete. It's continuous. But now let us consider a kind of discrete language. Then you need to sum psi n x, psi n x0, e to the minus lambda n t. And then you need to multiply by e to the minus u of x 2t. This comes from the transformation from psi to phi, plus u x0 over 2t. So this is an initial condition. These are the decay modes, etc. And these are from the transformations from psi to phi. Now let us look at the long time limit, t to infinity. You see what happens here? All these modes decayed, except for one mode which is 0. So this guy in the long time limit, you just take n equals 0. So I have psi 0 x, psi 0 x0. This is this energy. So here I'm using e lambda n t goes to 0, lambda n not equal 0. Here this guy will be 1 because I'm looking at the lowest mode. And here I have e ux over 2t plus ux0 2t. Again, I'm not deriving this. I'm just giving you the solution after all these things, and then you have this plus and the minus. I'm just telling you this. And this guy gives you, let's now use the ground state. So what is the ground state here? What is n equals 0? Psi n is proportional to e psi squared over 2. That's the ground state of the quantum problem, right? It's just a Gaussian. Boring Gaussian. So if we plug it in here, let us look what is this in the original units. I go back, where is psi? It was somewhere on the blackboard. What is this psi squared? This is e to the minus gamma x squared over 2d. And this guy is nothing else, if I recall the definition of gamma, of exponential minus m omega squared x squared over 2k Boltzmann t. This has to be 4 minus half. This times half. I think here I have a mistake. The point is like this. You see this guy times this guy give you simply exponential minus half m omega squared x squared over k Boltzmann t. The infinity is time t infinity. While these two guys, because here I have a minus and here I have a plus, remember this is the potential, they cancel. So what I get is what I expect. The long time limit, the solution is time independent and is equal to the Boltzmann equilibrium. This I already said, this is what we expected, this is obvious. But now we understand better why this happens. It happens because one of the eigenvalues is equal to 0. We understood the mechanism of this. And in fact, this is more general. Whenever you have a confining field, you will see that one of the eigenvalues is 0, which allows you to equilibrate, provided that the initial potential was binding such that you get eventually some equilibrium. I mean, again, if you have an open system with no field, then of course you don't have equilibrium. So this is valid because this potential is confining. Otherwise you have different behaviors. Okay, so here we will stop. I checked your homework. Some guys of you didn't understand, I think, that when you do a numerical problem, you need to do a numerical problem. That means you go to a computer and you need to simulate this, because some people just plotted what is expected or whatever. I don't know exactly. Maybe you have a problem with you don't have a computer, or you don't know how to program, or I don't know exactly what is the problem. But if there is a problem that you don't have access to a computer, you should talk to me, or you should talk to Yossi. I actually don't understand exactly what's going on. So some people simply didn't want to do it, but I don't know why they didn't solve these problems. I have actually your exercises upstairs, but I forgot to bring them, so I'll give them to you next week. I'm sure you can wait. But in the meanwhile, please, I want to write down what is the homework for the next time. So you again go to my webpage, and then there is chapter 2. Chapter 2 deals with first passage times and random walks on lattices. And from there, please solve these problems. This is only for the cubic lattice. There are two parts. You don't need to do both of them. So this is for the cubic You can do one of the examples. You don't need to do both. And then 217. Okay, so if there are no questions, I'll see you next week.